Welcome everyone, and thank you for joining us for today's webinar, Unparalleled Graph Database Scalability, delivered by Neo4j 4.0. My name is Mara Lee, and I'm part of the webinar team here at Neo4j, and I'm joined by Pat Wall, Director of Product Marketing, and our special guest, Dr. Alessandro Negro, noted graph database author and Chief Scientist at GraphAware. A few housekeeping items before we get started. We invite you to submit any questions you have throughout the demo using the Questions tab located at the top of your screen. We'll answer as many questions as possible at the end of today's presentation, and if we don't get to them all, someone on the Neo4j team will reach out to you directly. With that, I'll go ahead and hand it over to Pat.
Awesome. Thank you so much, Marilee. Welcome, everyone. We're really excited to have you here. So let's get started. Let's talk a little about scale in Neo4j. So Neo4j. The first thing I talk about is really when you're building a next generation application and you're using a graph database, there's really four areas where we think our customers are really seeing success. And where they're seeing the first is outbound scale. So applications need to be able to scale up and scale out. They also need intelligent learning. And what I mean by this is AI and machine learning. They need the ability to have data science incorporated into these systems. They also need to reveal context. And what I mean by context, I mean really finding the insights and finding the correct things in real time for their applications. And also they need security and data privacy, ensuring that data protection and regular compliance is across the entire application. But right now I want to focus on scale. So let's talk a little bit about scale. So as many of you know, Neo4j just released 4.0, which we believe is probably one of the largest investments in graph databases. And a big part of 4.0 was scale. And really, when we talk about scale, we're talking about three things. We're talking about sharding. Neo4j has the ability to shard now. We can actually shard the graphs into multiple to make it much more usable. We can also do federated queries. So you can query across those shards and find really interesting insights and design that database for you. And then finally, it's multi-database. It's the ability to take multiple shards and multiple databases and have it in one Neo4j instance. So I'd like to show you a couple examples of how we're doing sharding and how we're doing scale at a few organizations. So the first one is actually not even using 4.0. It's actually just using Neo4j and finding the right data at the right time and helping organizations scale. So if you're not familiar with it, but Adobe Behance is a social network of around 10 million graphic artists. And what they do is they really use this as a way to find information and find work by showing their resource and showing their work. And so what happens is there's massive updates, tons of reads and writes. So Adobe built this, and they're really interested. They're saying, let's try with 120 Mongo instances. And it worked, but it was slow and very costly. So they said, we can do better. So they said, okay, we shrunk it down to 48 Cassandra instances, but it was still too slow and a lot of IT overhead. So what happened was they came to Neo4j and we worked with them and we were able to shrink that to 3 Neo4j instances. So what did this do for them? Well, this was able to help them save money and also find the right data. So they were able to save over $500,000 in AWS fees and hosting fees. But also, they will reduce the footprint from 50 terabytes to 40 gigabytes. And the reason why is because they were taking the right data. They were actually looking at the connection of data, and it really helped them out. And so that was one really great way we helped Adobe scale their process. The next one I like to talk about is a photo sharing company. And this one really excites me because this is 4.0 in its best and brightest. So one of the largest photo sharing companies in the world uses Neo4j. Millions of users update photos every day. And so they are loving Neo4j, but they wanted more. They wanted more data. They wanted to access messages and likes and comments. And so they also want to understand the data by region. So they became an early adopter of 4.0. They brought this in, and we'll show you a little bit of how they worked with us. So the current state of their application prior to 4.0 was they had users, those users posted collections, and in those collections were photos. And very similarly, users follow other users. And they were analyzing this, and it was really great. But one of the things they came to us and said, hey, we need more. We want to analyze different parts of the graph. We want to analyze messages between different users. We want to say how users comment on different photos and collections. And we also want to see how users like other photos. So what happens is when you bring all this data in, it brings a lot of connections, but the value also grows as well. So when you just look at users, you're seeing about 10 to 100 million connections. But when that grows and you bring in comments, because users can comment on different areas, that grows to 100 to 1 billion connections. And then when you grow messages, you can even go further, because messages, you can message different users, you can message on comments. And the most data, the really valuable data, is likes, because you can like a user, you like a comment, you like a photo, a collection, a message. And so you can see this exponential growth. And so one of the things is how we actually help them do this. So what we did was we worked with them, and we were able to take their massive data set, and we said, hey, let's shard this by region. Some for GDPR, but other reasons just for this. So we were able to help them shard the data into North America, Europe, and Asia. So it was a really great way of helping them take this large data set, shard it across, but also be able to query across these shards. So without further ado, I want to pass it over to GraphAware to talk a little bit about how they're using Neo4j in some of their use cases, and also show a demo with using COVID-19 data. One thing we ask is if you have any questions and answers, I see there's a ton happening right now, please continue to ask them, and we'll get them at the end. So without further ado, I'd like to pass this over to Alessandro.
Cool. Thanks, Patrick. So let me start by saying that since at GraphAware, we support companies to succeed with their graph projects, and a lot of them have big graph databases to handle, you can imagine how much happy we were when Neo4j introduced such a set of amazing features. But this is not the reason why I'm here today, because I'm also the author of the Manning's book, Graph-Powered Machine Learning. So today, I'm going to be talking about the role that graphs are playing in the machine learning panorama, and how critical can be a feature such as, for instance, sharding to help our customers to deal with big databases and succeed in their machine learning project. So let's start by seeing, let's say you're talking about the reason why graphs could be your best friend while you are working at your machine learning project. And we will do it by considering 4 of the major challenges that almost any machine learning project has to deal with during its life cycle and once it is released. One of the most critical is the source of truth. Since it is the training data set you use to create the models for forecasting. So the quality of your models will be related to the quality and the quantity of data that you have. The second challenge is the performance. And here, I don't mean only the accuracy of the model, as usually referred for the machine learning project, but I'm referring also to the speed at which you can update your models and provide the forecasting. Because, for instance, if you have the best algorithm for recommendation, but it takes minutes instead of milliseconds to provide the recommendation, it will be totally useless. And directly related to the performance, there is the way in which you actually store the models that you will use for providing forecasting, because the speed at which you will store it and access to it will impact your performance. And finally, of course, the way in which you communicate the results of your analysis is critical in a lot of scenarios. So starting from these challenges, graphs provide support in each of those. And specifically, graphs can be used to create a single connected source of truth, a knowledge graph that gather data from a variety of different data sources. Thanks to the schema structure and the data model based on simple concepts such as nodes and relationship. And then on top of it, you can perform cleaning and merging. You can enrich it by using external source of knowledge. And at that point, you can extract features thanks to the fast access patterns. Graph algorithms can help you to improve the accuracy of your model either alone, that means as a key algorithms in your pipeline, or in combination with non-graph algorithms. While in terms of speed, storing your machine learning models in a graph gives you the opportunity to store more than one model and access to them in a very efficient way. Since in a graph, every single node and every single relationship is an access point. So you have multiple access points, multiple access patterns to your model. So graph visualization instead is a very powerful tool, specifically for big analytics projects where analysts are your final end user, but not only. If you think, for example, at the Panama Papers use case, the journalists were able to perform their deep analysis via graph visualization using Linkurious and Neo4j, but at the same time to communicate it publicly in the right way. So in this context, how can shards help? Well, definitely in terms of different ways. But let's focus on the most critical, at least in my opinion. First of all, sharding simplifies and speeds up the creation of big graph databases because you can split these big graphs in smaller graph databases, and then you can access to them in isolation. But at the same time, sharding provides proper data isolation because, as we were discussing before, this single connected source of truth is the result of the gathering of multiple data sources in this single instance. But of course, you have to keep data isolation to enforce security and data privacy. And even in this sense, sharding can help you to accomplish this specific task. Moreover, sharding increases the performance, of course. This is one of the main reasons why it has been introduced. Because you can, by splitting these big graph databases in multiple smaller graph databases, you can access to them in parallel, both during reading and during writing. And so you can speed up quite heavily the performance of your application. And finally, it allows you to decouple the training data, this single connected source of truth, from the, let's say, model data that you will use to provide your forecasting. And I'll make these concepts even more clear by considering a few concrete examples, a few concrete scenarios, and also a quick demo. And let's start with one of my favorites, actually. Suppose that you would like to monitor a subject. And this subject can be a terrorist, can be your wife, if you prefer. And you would like to do it for different reasons. And you would like to create a model for predicting where he or she will be in the next hours, days, or months. And of course, so you can do this by using something that you know for sure that they will bring with themselves almost all the time, their phone. So let's see what is the data that we can use, or what are the data sources that we can use. So as you know, phones continuously try to communicate with as many cellular towers as possible. So as you can see in this example, you can be connected to 1, 2, 3, or even more different cellular towers. And these cellular towers actually store all these logs in a way like this one, where they keep track of all the devices that are connected to the cellular tower. But of course, in this way, this data is very hard to use. So this guy from the MIT had a very, very nice idea of organizing this data for each subject in the form of a graph, where each node is a cellular tower, represents a cellular tower, and the connection between two towers happened if at some point in time, the phone was able to connect to both of them. And so the weight in this sense is the amount of time, the percentage of time in which the phone was able to connect to both of them, actually. So once you have this graph that is created for each of the monitored subject, what you can do is to start, let's say, organizing this graph by clustering it. And as you know, Neo4j provides you a lot of opportunities for community detection and clustering, such as Louvain or label propagation. And in this case, what we can get is this split of the graph in multiple shards. And of course, since you know the position of the cellular towers, you can recognize where is the school, where is the market, where is the church, the office, and so on and so forth. And let me stop for a second before moving into the model and discuss how much useful it will be to have sharding in this sense, because this is a perfect use case for sharding, because you can have a shard for each of your graph, because it is totally independent from all the others, and this can heavily speed up your analysis. That in this case will create as a model this Markov chain, where each node in this case is a location. So as before, offices, homes, and so on and so forth. And the relationships express the probability of the transition from one place to the other. So in this case, for instance, we have a 50% of chance that if the subject is in the office, that will move to the back home. And these guys also wanted to improve this model by creating multiple Markov chain because, of course, your behavior, the subject behavior will be different if it is a normal day, a weekday, or it is a weekend, or if it is 6 p.m., or if it is 9 p.m. Or 9 a.m. in the morning. So they created multiple contextualized Markov chains. And again, in this case, you can store all of them in one or multiple shards, increasing quite a lot, again, the performance. As a second scenario, let's suppose that you would like to implement a mobile application for which recommends movies that user can watch in a cinema. So in this case, you don't want to have a classical recommendation, but you would like to have a contextualized recommendation because you know where is the user, what is the location, who the user is with, and even what is the time. So actually, in this specific case, you would like to change the suggestion according to this contextual information, because of course the preferences can change if the user is alone, if he's with his wife or with the kids. And this means that if before we had a simple user item dataset, here we have a multi-dimensional matrix in which we have to take into account also the contextual information like time, location, company. So in terms of graph, instead of having a classical bipartite graph where you have users and items connected via this relationship representing the interactions, you have a database like this, in which you have that the events are represented as a nodes. They are, the watching events, and they are connected to all the contextual information that were in that specific moment when the user was performing this selection. And if you're using collaborative filtering, even in this case, you will have multiple similarities between the items and users according to the specific condition in which the user was at that time. Again, even in this case, for this specific scenario, you can store all this information in multiple shards because in the greatest part of the case, they are fully independent or can be treated as independent graphs. And this will give you the opportunity to treat them as isolated elements or in a combination, because you will be able to access to all of them at the same time in a very efficient way. So let's say that as a third scenario, I would like to talk about something that is affecting our life since a while, actually. As you know, I'm talking to you from Italy, where we are locked at home since almost 1 month. So in this case, suppose that you would like to help the research community by organizing all the knowledge about coronavirus to help scientists to fight it. So in this case, what we have done was to gather the data available about coronavirus. Specifically in this demo, we will consider this core dataset that collects all the papers available about coronavirus, and we enriched it with other data sets already available, such as UniProt, that contains a lot of information about proteins, their relationship with genes, and so on and so forth, and Ethernet, that is also another interesting data set connecting genes with anatomies part, or with genes and diseases or pathways, and so on and so forth. So let me start with the demo, in which we will use GraphAware ecosystem. That is a a graph-powered insights engine capable of gathering data from a variety of data sources, analyze the unstructured part by extracting entities, keywords, and relationship among entities, and also to organize all of this in the form of a knowledge graph that is easy to navigate and explore. And the idea is that the result of this can be delivered to the scientist to work on this knowledge in a single unit. So let me share my screen. So this is the interface that allows you to access all the human features, capabilities. Again, let's start our journey from the data sources that, of course, are the initial part of this demo. So via the resource management interface, you are able to define all the data sources that you would like to use in your environment, as well as the data storage that you would like, where you would like to store the data that will be the result of your analysis, for instance. So in this case, we have some local file systems. We have where we stored all the JSON files available regarding the coronavirus papers. Then we have this UniProt dataset that is available as an Amazon S3 bucket. And even the format can be different because some of them are in JSON format, other are in TSV, other in CSV, and so on and so forth. Moreover, as you can notice, we have also some of the more than one actually Neo4j instance, because we are fully supporting Neo4j 4. So we can specify what is the shard or the database, if you prefer, on which we will actually store the result of our analysis. We have more than one because we would like to split these big graph databases in more than one, and then we will see how we can treat all of them as a single unit. On the other side, we have also the skills. The skills actually allow you to, let's say, process the unstructured part of your data, in the sense that you can take this textual data and extract entities, as it is done from this bio pipeline, that extract entities such as proteins, genes, or other diseases, molecular functions, and so on and so forth. While the text rank pipeline is used as an intermediate step, because we need it for the third skill. In this case, what happens is that we decompose the text in a lot of type dependencies and tokens that will be used by the extract keyword skill for recognizing autonomously small phrases or single words that represent the content of the text, so that you don't have to read fully the article. So once you define your resources and your skills, what we have to do is to import the data or define multiple workflows to import and process this data. So let's start with the UniProt case. In this case, of course, we are talking about structured data. So via the orchestra, that is our workflow engine, you can define how you would like to get your data in and process it. So in this case, we are taking the data from S3, and then we are decomposing in multiple JSON files. And then via a Cypher query, we can convert the JSON structure in our desired graph structure. And the result will look like this at some point. On the other side, we have also the Ethernet dataset. Again, another interesting structured dataset in which here we have a TSV file that will be imported as nodes and relationship in the graph database. Again, we will have in this case, it will be a much simpler graph mapping, and the visualization will be even nicer in this case because we applied some layer of style on this, and you can recognize how many, entities and relationships you have in this case, so that you can double click on here and you can navigate these, let's say, different anatomies, and then you can explode them in the, let's say, in the graph, actually. So let me then go back and let's talk about the most interesting part, because of course we don't want to process only the structured part, because we would like to extract from the text entities and so on from the papers. So in this case, we have more than one workflow because we can, of course, we have to ingest the data from the JSON files available. And again, here we have the Cypher query that will perform this task. But here, in this case, we wanted to extract the entities. And so we have a little bit more complex structure in which we extract entities from the text using the bio pipeline described before, passing the text that we have, or from the abstract, again, using the same skill, but using the abstract in this case. And again, this information will be mapped back in the Neo4j. And the result will be a schema in which we can visualize the data that will appear like this. We have still keywords, we have the entities extracted, and so on and so forth. So just using the interface, we were capable of just ingesting, but also processing all the textual data. And as a final point, I wanted to show you the features related to the sharding facilities available in Neo4j. So in this case, we created this knowledge graph that wanted to organize the wall of knowledge. So we created a simple schema in this case, where we have data coming from all the shards that we have. So we have paper from the, let's say, the papers dataset. We have the UniProt proteins, and we have some of the gene coming from the Ethernet dataset. And the result can be accessed using one of the most interesting features available in Hume, that is these Hume actions that are actually user-defined function that you can define using this interface and specifying the query that you would like to run. And as you can see, even though this is a little bit complex query, but you can you can see the power of this query that is spanning across all the shards that we have, and the result will look like this. Of course, now we are querying all the shards, and we are accessing to all of them at the same time. And the idea is that we can give this knowledge graph in the hands of the, let's say, of the scientists that can start their analysis considering not only the papers, but also Ethernet database, UniProt. And we are going to add more and more data sets since it is very, very simple to ingest the data, process the text, and extract the entities, for instance, or the keywords, and then use all this information to properly access to all of them. So this concludes my demo and even my presentation, actually. So it's been a pleasure talking to you today. And feel free to ask any questions that you have or here, or just drop me an email. Thanks.
Awesome. Thank you so much, Alessandro. That was really great. We have a ton of questions. Let me go through this and try to find a couple that are here. Okay, here's one that's been coming up quite a lot. How flexible or complex is it to write a query that spans across multiple shards?
Well, definitely it's not super simple as doing a simple query, because you have to respect some rules related to the, of course, migration from one shard to the other. But definitely, once you get used to it, it's very, very straightforward. And actually, it is even super powerful, because if you write the query properly, you can even leverage the, let's say the parallel processing available in the sharding capabilities. So you can access to all these shards in parallel and then get your answer. So it is not as simple as the classical Cypher query, but definitely the results worth the effort, definitely.
Awesome. Thanks so much. So one of the questions says, when will Aura be upgraded to 4.0? So for those who don't know, Aura is our database as a service. It was launched a few months ago, and we're working on it right now, and we should have Aura updated to 4.0 within the next few months. So there's my answer. And I think we have time for maybe one more question. So I think let's keep going through this. I think here's a great one. It says, how can we use the results of the work that you're doing about coronavirus?
Well, we will make the database available soon. So as soon as we will complete all the analysis and the integration of different data sets, we will make it available as a Neo4j database that anybody can just download and use as they prefer, actually. So it will be available as a Neo4j database.
Awesome. Excellent. Alrighty. Well, thank you so much for attending. We really appreciate that. I know there are a lot of questions that we didn't get to. If you did have a question, don't worry. Someone from Neo4j will be reaching out and helping to answer your questions. So without further ado, I'd like to say thank you and have a great day.
Thank you.